when I look at these steel balls collectively, they function as just a simple pendulum. So if I give this system a certain amount of gravitational potential energy by doing work against the force of gravity, and I release the steel balls, they swing back and forth just like a pendulum inside of a clock. And it'll actually keep swinging back and forth like this for quite a long time. But the more interesting phenomenon that we can observe here is when I just take a single steel ball. I've once again done work against the force of gravity, so it now has gravitational potential energy, and I release the ball and it collides. We can see that momentum is being conserved here. Momentum is just the product of mass times velocity. So if this ball on the far end is moving with the same velocity as this incoming steel ball here on the opposite end, we know that all the balls have the same mass. And it makes sense that if momentum is conserved, we have this single steel ball raising up to the same altitude, more or less, the same height at which this incoming ball originally fell from. And of course, it's not a perfectly elastic system, and there's energy loss here due to heat and due to friction, so eventually the entire system comes to a stop, or else, it will keep swinging on forever and forever, and we know that the second law of thermodynamics prohibits that from ever happening. But there's more going on here than just conservation of momentum, because if you think about it, if I just have this one ball coming in at a certain speed, v, there's no reason that I couldn't have, let's say, two balls then come off from the other end, moving half as fast as this incoming ball, right? In that case, momentum would still be conserved. And what you can observe, at least on the macroscopic level, but what's happening, on the actual level of collisions, the interaction among these steel balls, is that there's a sort of compression amongst them. And that's what kind of generates this energy, which is going to traverse along this series of these steel balls, right? We know that they're barely touching one another until it gets to this last steel ball, where that energy, which has been conserved throughout the series of collisions, then has nothing to collide with, so that kinetic energy once again gets converted into potential energy as this ball gains height, and then it falls back down again, and we have another series of collisions which converts the energy in this steel ball then back once again to this steel ball. But once again, as I was saying, the kinetic energy can't explain everything because there's an infinitely possible number of solutions. We know that kinetic energy is half, right, mass times velocity squared. So these balls all have the same mass. So if this steel ball is coming in with velocity v, kinetic energy conservation alone is not going to explain why it's only this ball on the far end that's moving. Right? Like, why doesn't this ball just come in and then all four of these steel balls move off with some sort of a kinetic energy that's equivalent to the kinetic energy of this incoming steel ball? And the way that we can think about this is actually as a series of infinitely fast collisions between this first ball that comes in, collides with this second ball, which then collides with the third ball, colliding with the fourth ball, colliding with finally the fifth ball, which doesn't have anything to collide with. So it then moves, as I've said before, it gains potential energy and moves out like this. Now, the more interesting phenomenon is when we take two of these balls. Now two balls come off from the opposite side. Well, we could still satisfy conservation of momentum by saying, okay, I have these two masses coming in with a speed v, so how come we have two balls moving off over here? How come I don't just have one steel ball moving twice as fast? In that case, momentum would still be conserved. And we could also have, various relationships amongst speed, right, velocity, and I could conserve kinetic energy by only having this one ball move out, or I could even have, all three of these balls move out, and I could still, in some way, conserve momentum and kinetic energy. So there has to be something else going on here. And once again, if we think about this as a series of small collisions, it looks like these two balls hit pretty much simultaneously, right? We think of these as kind of one mass. But in an amount of time that appears, of course, as I said, on the macroscopic level, we can't observe this, but this second ball will actually collide with our system a little bit later than this ball right here. So I have this ball colliding, and then, in an instant later, then this first ball will collide with the system. So when ball number 2 comes in and collides, right, we get this first ball moving out, and it's going to move up with the same velocity that this ball had coming in here, because we know that kinetic energy in this case, is maintained, momentum is conserved, and then as this ball moves out, we have this second ball come in and collide, and then that causes this next ball to move out. So that's why when I displace these two balls, I have two balls come out on the opposite side instead of just one moving twice as fast, or instead of, three moving at a smaller velocity. It's because we can think of these as actually a series of separate elastic collisions. It's a difficult concept, and it's something that can be explained more thoroughly with differential equations, and I'm not obviously going to get into that. If I take three balls and displace it, it's the same kind of phenomenon, except the third ball now is constantly in motion. Because when I have these three balls strike, right here, I can think of it this way. It's three separate collisions. This one first, so this ball moves up. Then this one second, which makes this ball move up. And then finally, this last ball, which makes this third ball, which was originally part, remember, of the number of steel balls that was displaced. Now this one is also going to move up. So that center ball, notice, is constantly in motion, regardless of which side has been displaced. And there's some other little cool tricks that you can do, right? If I pull these both pretty much up to the same height and release them, when these balls collide, and this is a good example of Newton's third law, right? When one of these balls collides here, we get this equal and opposite force that basically checks the motion of this ball, and it ends up moving back in the opposite direction. And I can double the amount of mass, and I can see that the exact same Newton's third law still holds in this case, right? And it gets a little bit messy. But there we go.